Hello, I am Lars and I will talk about B coloring parameterized by Clique-Width. This is a joint work together with Paloma Lima and Daniel Lokshtanov. Okay, so first let me explain to you what a B coloring of a graph is and where this notion comes from. So it originates from the analysis of the following heuristic for the graph coloring problem. So let's consider this graph. And what we do first in this heuristic is that we assign a unique color to every vertex. This way, of course, we have a proper coloring of the graph. And now what we want to do is we want to get rid of the colors one by one while keeping the coloring proper. Okay, so for example, first we try to get rid of this brown color. Then we remove the brown color from this vertex, and now we want to reassign a new color to that vertex in such a way that we do not create any coloring conflict. For example, we can give it color purple, and like this, we still have a proper coloring of the graph, and we reduce the number of colors by 1. Okay, similarly, we can recolor this vertex that has color light blue with color red, and we still maintain a proper coloring. Also for this pink vertex. Okay, so now we're down to these 4 colors, and let's try to remove color blue. So there are 2 vertices now that we have to recolor, but we see that when we look at the middle one, this won't be possible, right? Because this vertex already has a neighbor of all the other colors. So we cannot assign a different color to this vertex than blue without creating a coloring conflict. All right, and this is what we call a B vertex for color blue. Okay, so when does this heuristic stop? Well, I mean, of course it stops when every color class has a B vertex. Right, because if a color class has a B vertex, we cannot get rid of this color class. Therefore, if all color classes have a B vertex, we cannot get rid of any other color. And we see that in this example, indeed, each color class has a B vertex, the ones that are marked now. And in this case, when every color class has a B vertex, we say that this coloring is a B coloring of the graph. And here we have a B coloring with 4 colors of the example graph. Okay, so just to list the first definition. So a proper vertex coloring of a graph G is a B coloring if every color class has a B vertex. And remember that a B vertex is a vertex that sees all the other colors in its neighborhood. Now the B chromatic number of a graph is the maximum number k such that G has a B coloring with k colors. And note here that we are interested in finding the maximum number and not the minimum like in the usual chromatic number of the graph. And the reason for that is that if we define the B chromatic number of a graph in this way, then in the worst case, we see that in the worst case, the coloring heuristic that I just described will produce a coloring with B chromatic number many colors, right? Because the heuristic stops whenever we reached a B coloring, and the B chromatic number tells us the largest number of colors that we have in any B coloring of the graph. Right, and one thing we can immediately observe is that for any graph G, the B chromatic number is always at least the chromatic number. And this is because, well, if you have a proper coloring of a graph with the minimum number of colors, then this always has to be a B coloring, right? Because if it isn't, then we could decrease the number of colors by 1. Therefore, it was not the best possible coloring to begin with. Okay, So now we have seen that the B-chromatic number is always at least the chromatic number of a graph, but how big can this difference be? And it turns out that this difference can be arbitrarily large. So let's look at this example graph, which is a complete bipartite graph on n vertices each, and we remove a perfect matching. Okay, so in this picture, I only drew the non-edges here with these dashed edges, and all the other possible edges are present between the classes, of course. All right, of course, this graph, because it's bipartite, it has chromatic number 2 with a coloring like this, but it has B-chromatic number n, because we can just give, all the matched up guys by the matching that we removed the same color. And then like this, all vertices will be B vertices for their color. Because for example, if we look at the blue vertex on the top left, it is adjacent to all of the other guys on the right. Therefore, it will see all the other colors in its neighborhood, right? And this is true for every vertex, of course. Therefore, this is a B coloring of that graph, and it uses n colors. Okay, another difference that I want to point out with the notion of proper colorings is that, of course, if we have a graph G and it has a proper coloring with k colors, then it also has a proper coloring with k+1, k+2, and so on colors. Because I mean, if we just use more colors, if we introduce more colors, we cannot really destroy the proper coloring property unless we try, you know. Okay, on the other hand, for a graph G, there may be some number k that lies between the chromatic number of the graph and the B-chromatic number of the graph, such that this graph has no B coloring with k colors. And one good example is a graph that we have already seen. So it's k and n minus a perfect matching. And we can see that this graph actually has B colorings only with 2 colors or with n colors and nothing in between. Okay, so the problem that we are dealing with in this work is the problem of given a graph G and an integer k, we want to know if G has a B coloring with k colors. And already when it was introduced in 1999 by Irving and Mandelov, it was shown to be NP complete in general. Now, over the years, a lot of work has been done for this problem on graph classes. And so to the best of our knowledge, these are the results concerning the complexity of the problem on graph classes, where the top 3 in here, in these classes, it has been shown to be NP complete, so all the red ones. And in the lower ones, the problem has been shown to be polynomial time solvable. And now note that in this picture, whenever there's an edge between 2 graph classes, then it means that the upper graph class contains the lower one. All right, so if we look at this picture, there's we can see that there's a polynomial time algorithm for the problem on claw-free block graphs. So of course, it would be interesting to see what happens on general block graphs. And more generally, also, it would be interesting to see how the problem behaves on distance hereditary graphs. And both of these both of these problems have been stated as open problems in the literature. So one thing that we can observe is that almost all of these graph classes where B coloring is known to be solvable in polynomial time, except the case of large girth, all of these graph classes have constant Clique-Width. Right? And the main result of our work is that B coloring can be solved in polynomial time on graphs of constant Clique-Width. So therefore, this algorithm unifies and extends, almost all the known polynomial time algorithms on graph classes for B-coloring, again, except for graphs with high girth. And it solves these two problems that were stated in the literature regarding block and distance hereditary graphs. Okay. So concretely, we show that B-coloring, if we are given an input graph together with a Clique-Width W expression, then it can be solved in time n to the 2 to the O of W. Now, okay, this is polynomial for some fixed value of W, but of course, this is not a very nice polynomial because it has very, very high degree. So we should, of course, immediately ask ourselves, can we do any better than this? And actually, well, probably not much, at least. So first of all, as a consequence of previous results in the literature, we observed that, first of all, B-coloring parameterized by W is W1 hard, so we cannot expect any FPT algorithm. And furthermore, unless the exponential time hypothesis fails, we cannot even expect to get rid of the exponential dependence on W in the degree of the polynomial. So if we had an algorithm that runs in time n to the 2 to the little o of W, then this would already refute ETH. All right, another aspect of this work is that it was the first work that considered B-coloring from the point of view of structural parameterizations. So yeah, we also looked at the parameterization by the vertex cover number of the input graph, and we showed that it's FPT in this case. Okay, and then we also studied a related variant of B-coloring, namely the fall coloring problem. And the fall coloring is a B-coloring where every vertex is a B vertex. Okay, and then you can see that this is actually equivalent to having a partition into independent dominating sets of the input graph. Now we modify our algorithm and we show that fall coloring can also be solved in the same runtime bound. And we also show that we get the same types of lower bounds for the fall coloring problem parameterized by Clique-Width. So it's W1 hard, and we cannot expect to have an n to the 2 to the little o of W time algorithm unless ETH is false. Okay. So one thing that I want to mention also is that there are several vertex coloring problems behave very differently when we parameterize by Clique-Width. So the most famous graph coloring problem has been shown to be XP time solvable already in 1994, and it was shown to be W1 hard in 2010. But on the other hand, we can see that the list coloring problem, where we're given a graph and each vertex has a list of colors, and we're only allowed to use colors from the lists of the vertices. So this problem is already NP complete for graphs of Clique-Width at most 3. And the related pre-coloring extension problem is also NP complete for graphs of Clique-Width at most 3. And in the pre-coloring extension problem, we have a graph where some of the vertices already have received a color, and we want to know, can we extend this coloring to a proper coloring of the entire graph? All right, and interestingly also, last year it has been shown that the Grundy coloring problem is NP complete on graphs of constant Clique-Width. And this is a nice contrast with our result because the Grundy coloring problem also originates in the analysis of graph coloring heuristic, but in this case, it's the greedy heuristic where we process the vertices one after the other, and we always assign the lowest available color that we can give to a vertex without introducing a coloring conflict. So yeah, and then the Grundy coloring is the problem of finding a coloring with the largest number of colors that can be produced by this heuristic. And this is already NP complete on graphs of constant Clique-Width. Now, another variant of coloring is the Clique coloring problem, where we want to color the vertices of the graph such that we have no monochromatic maximal clique. And this problem, again, is XP, but it's not yet known if it's W1 hard or FPT. And okay, so in this work, we show that B coloring and fall coloring are both XP and W1 hard. Okay. So let me briefly explain some of the, like the main insight that made our algorithm work. And first of all, we will not work with the original definition of clique width, but rather with this notion of module width. But this is really, it's linearly equivalent to clique width. So yeah, this works just as well. And one thing before I continue is that it should not be confused with modular width, which is something else entirely. And to explain the main ideas of the algorithm here, I will only consider the linear variant of module width because, yeah, I will be able to communicate everything I want to, and it's not so technical. So in the linear variant, we have an ordering of the vertices of the graph. And at each position between two vertices, we look at the cut consisting on the vertices on the left side and the right side. Right? Let's call the vertex on the left side AI and the ones on the right side BI. And then the crucial property of module width is the following. So we have an equivalence relation on the vertices in AI according to their neighborhood in BI. Okay, so we partition the vertices in AI into these equivalence classes where whenever two vertices are in the same equivalence class, we know they have the exact same neighbors in BI. Okay, so for example, these four vertices have those neighbors in BI. Yeah, these three vertices have those neighbors, and so on. Now the module width bounds the number of such equivalence classes at each position I that we consider. And this is what makes it useful in algorithms. Okay, so first, before I talk about B coloring, I want to give the main idea of how we would solve the graph coloring problem on graphs of bounded linear module width. And of course, we do a dynamic programming along the linear order of the input graph G. And at each position I, we will always store information about proper colorings of the subgraph induced by the vertices in AI. And okay, so it will look sort of like this. Now, of course, there will be way too many colorings to keep track of, so we have to decide what type of information we will keep in order to reduce this information, but of course in such a way that we can still solve the graph coloring problem. And of course, the crucial aspect will be that at some point later on, we also want to color the vertices in BI. Right? And given a coloring, we want to determine which vertices in BI can receive which colors. Okay, so suppose that we want to give the vertex V color blue, and we know that there are blue vertices in these two equivalence classes here. Well, I mean, then all we have to do is to check whether the corresponding neighborhood of these equivalence classes contains V or not. And well, if V is in one of these neighborhoods, then of course we cannot give it color blue without introducing a coloring conflict. If, on the other hand, we have another vertex U that is outside of these two neighborhoods, then, well, we can safely give it color blue, and that will work out. Okay, and this is the essential information that we have to keep about the color classes, and nothing else, actually. So we only have to remember for each of the color classes, the set of equivalence classes of this module width equivalence relation, such that there is a vertex of the color C in that equivalence class. Right, so, and yeah, and of course there are at most 2 to the W many types, because we have W equivalence classes, and each subset of these equivalence classes gives us a new type. Now suppose that we have 2 colors with the same type, here blue and red. Then we don't really care anymore about the names of these colors, blue and red. We only have to remember that we have 2 colors, 2 color classes that have this given type. Right, and this is how we can reduce the number of, we can reduce the information to keep track of to give an efficient algorithm for graph coloring. Because so the information that we need to store about one given coloring is just its signature, which will be a function that tells us for every type, how many color classes of that type do we have. And well, we have 2 to the k types. So of course we have at most 2 to the w, sorry. So of course we have at most n to the 2 to the w many signatures. Okay, but how to incorporate information about B vertices now? So suppose that we have this vertex V here, and it's supposed to become a B vertex of color blue when we are done in the end with the algorithm. Then, well, the first idea is that probably comes to mind is that we can just remember where this vertex is sitting and which of the colors it has already seen. So for example, maybe it already has some neighbor of color red, but it still needs to have a neighbor of color yellow at some point in the future. But of course, this does not work because we would have to remember the names of the colors, right? So there will be too many options, and well, we have already forgotten about their names, so there's really no way that we can make this work. So then maybe the second idea would be to remember again where it sits and how many color classes of each type it has seen. But if you think about this for a moment, this also doesn't work for the following reason. So suppose we have 2 colors, here the dashed color and the dotted color, and vertex V already has a neighbor in one of them. Right? And then later on, we will encounter a vertex that we will add to a color class of that type. Then, of course, since we have forgotten about the names of the color classes, we will not be able to distinguish between the case if we add it when we add it to the dashed color class or the dotted color class. So yeah, this approach also doesn't work. Okay, so now let's see what does work. So what we can do is sort of a, we switch the perspective. Instead of looking at the vertex B and we say it still has to see certain colors, we look at the color class yellow and see that color class yellow has to do something for vertex V to become a B vertex of color blue. Right, so in particular, we can store at this point that color class yellow still needs to contain a vertex from the neighborhood of Q in order for V to become a B vertex of color blue. Right, so we can sort of store the information that color class yellow must contain a neighbor of Q later on in the algorithm. And then if we do this and we run our algorithm, and at the end of the algorithm, and we call this sort of the demand to the future of an equivalence class Q. Right, so if we run our algorithm and we see that in the end all the demands have been fulfilled, then we know that all the vertices have become B vertices. Right, and this is why we can make this algorithm work. So what is the information that goes into the type of a color class C? So for each equivalence class of the module width equivalence relation, we store that either this equivalence class has a vertex of color class C, or color class C has demand to the future of this equivalence class, or none of the two. And then we can, of course, see that there are at most 3 to the W such types, and at most n to the 3 to the W descriptions of colorings that we have to keep track of. And yeah, so this is the basic idea. Then, of course, to make this work, this gets a bit technical, but yeah, this is the most crucial insight. So in the end, we show that B coloring can be solved in time n to the 2 to the O of W if we are given a Clique-Width W expression of the input graph. All right, so I want to conclude with some further work. So we have shown that B coloring is FPT parameterized by vertex cover, and it's W1 hard parameterized by Clique-Width. Yeah, so of course, the natural next question to ask is about the most famous parameter sitting in between the two, which arguably is the tree width. So we expect that for tree width, the problem should be W1 hard, but yeah, we haven't proved it. Okay, so the next question considers the vertex cover parameterization. So under the exponential time hypothesis, there is a 2 to the little o of k log k poly n time lower bound for B coloring, and our algorithm runs in time 2 to the o of k squared log k. So of course it would be interesting to close this gap. And we believe that a 2 to the o of k log k poly n algorithm should be possible. But again, we haven't found it yet. And lastly, what about other structural parameterizations? Right, so in particular, it would be nice to see some FPT results for certain generalizations or relatives of vertex cover. Okay, that's it. Thank you for your attention.